This video is brought to you by Hagromo Chalk. Use code TPSA 10% off to get a discount.
Hello, my name is Niall and today we'll be doing a tutorial on the quantum approximate optimization algorithm. This is part of the lecture series provided by the TPSA for the Qiskit Fallfest 2025. So, what we'll be doing is we'll be going through a full Qiskit notebook that implements quantum approximate optimization algorithm for the max cut problem. And hopefully you've seen some of the previous videos in our lecture series, but if you've not, we'll be taking it nice and slow so you can understand every concept that you will see in this notebook. So first, what we'll start off with is an overview of variational quantum algorithms. These algorithms are called hybrid algorithms, and that means that they use a quantum computer and a classical computer. So, for a given problem, we will generate a parameterized quantum circuit, and all that is a quantum circuit that depends on a free parameter, and in this case, theta. This is also called an ansatz, and what an ansatz is a good structured guess on what a solution to our wave or a solution to our problem would look like. This can be based on the structure of the problem as well as other attributes. We'll run this quantum circuit and we'll receive some results based on our measurement. And with these results, we'll pass them through a cost function. And so this will tell us how good of a solution we've generated based on our quantum circuit. And based on that cost function, we can optimize over our free parameters, theta in this case again, such that we can run the quantum circuit again, evaluate it with our cost function, and determine if it is a better or worse solution, and continue on this loop until we've achieved a satisfactory result to our problem. So first, what we'll do is we'll go through what the max cut problem is. It's an optimization problem where we need to look at a graph and separate it into two groups. So first, we'll run some code to generate a simple graph so we can understand what the max cut problem is. So for a given graph, there's going to be a number of nodes, in this case 5, with edges. And edges just connect to different nodes. And what the max cut problem says is that we need to label or group these nodes into two groups. So for this case, we could color each of these nodes in either gray or purple. And if two nodes are of different colors, the edge between them can be determined to be cut. So if 0 is gray and 4 is purple, we can cut this edge and we can count that towards our solution. What we want to do is we want to find a solution of labeling each of these nodes that maximizes the number of cuts. And the problem with these kinds of problems are they're NP hard. And that means that the number of solutions that are possible are very, very large. But we need to determine the most optimal solution. So in this case, a solution to the problem is that there's only, you color all of our nodes gray, and we color number 4 purple, and then that would mean that this edge is cut and this edge is cut. But there's other solutions that have more than 2 edges cut, and we want to find these solutions. There's 2 to the n minus 1 possible solutions to this problem, and that's why these problems are well suited to quantum computers, because there are many, many solutions that need to be represented for very, very large graphs. And so what we can do is we can create a mathematical formula for this problem. So as before, we want to make an optimization on a function. In this case, what we're going to do is we're going to constrain it to binary values. So our x in our function can only be binary, so 0 or 1. In this problem, what we're going to do is that every pair of nodes, so in this case it could be 0 and 4 as one pair, for all the different possible pairs in a function, there's going to be a corresponding edge, as before, ij, and we need to determine if that is cut. So we'll use this function here to determine if it's cut. So it's only 1 if either x or j is 1. So if the edge is in a cut and 0 otherwise. And so what we'll do within the whole problem is that we will try to minimize this function here so just multiply it by -1, so that the number of edges traversed by a cut is maximal. This is just a mathematical formulation to start off with. The next part is that we need to convert this into a problem we can run on a quantum computer. And so we use this reformulation that we call QUBO, quadratic unconstrained binary optimization notation. So what this will allow us to do is allow us to rewrite our problem as a Hamiltonian. And Hamiltonians are things we can simulate on quantum computers. So first we'll start off with the QUBO. So the QUBO is just going to be a vector x, and that's just going to be a series of zeros and ones. As before, it's going to be binary, multiplied by this large matrix of real numbers. So this matrix is going to formulate our problem, and then we're going to multiply it by our solutions, which are going to be our x vectors. And so they're going to be a series of zeros or ones based on the problem. So the binary variable is going to indicate which side of the cut a node is on. And then for each edge, as before, we have the formula that's going to solve the problem. If it's, and it will equal to 1 if the nodes are in different sets, i.e. 1 is grey, 1 is purple, and 0 if they're in the same set. And what we'll then do is we'll convert this into the Hamiltonian as before. So what we're going to do is we're going to, rather than using zeros and ones, we're going to use spin variables. And all that is -1 and 1 compared to 0 and 1. And this is just to allow us to use the Pauli Z operator, which can be used on a quantum computer. So you can see that is listed here. So Pauli Z operators. And this is just a small reformulation of our problem. So the mathematics is listed here. It is possible to convert our Hamiltonian from the QUBO problem into the one that we want, based on some steps that you can see. And so let's just restate our problem in terms of these Z operators, or sometimes called spin variables, where we 1 and -1 rather than 0 and 1. We'll let each vertex of the graph, so the vertex just being nodes, be associated with the ground state or the excited state of our qubit 0 or 1, where the value denotes the set that the vertex is in. So 0 can represent grey and 1 can represent purple. And as I'll say many times throughout this tutorial, we're maximizing the number of edges where there is one node that is in one group and the other node is in another group. And when we multiply our Z operator, so our Z operator is hidden down here, that's this matrix here. When we multiply it by the ground state, we'll return the ground state and an eigenvalue of 1, that's just omitted. And when we multiply it by the excited state 1, we'll return the excited state and an eigenvalue of -1. So this is a great way to formulate our problem, because if we multiply the two edges by a Z operator, if it is equal to -1, as is said here, we know that there is a cut between those two nodes. And that allows us to write our whole Hamiltonian as this very simple Hamiltonian, where we've two different nodes and some large matrix. And so what I haven't stated so far is what this large matrix is. In this case, we're just going to list it as an unweighted graph. So if we scroll up to the graph we had before, each of these edges are of equal value. So the great thing about this problem is that you could make these different edges more valuable, and it would only increase the problem in complexity ever so slightly for the quantum computer, but exponentially for a normal computer, because it has to optimize over different weights of these edges. And so what we'll do is we'll create a function that we'll use later on in this code tutorial. So for the max cut, there's no single qubit bi terms, because each edge maps to a term zi, zj. So each pair of nodes can be mapped to an I and a j, where there's an edge in between them. There's no edge just sticking out. And their coefficient is going to be equal, so the weight is going to be equal to the weights of our graphs. So in this case, it's just going to be 1. And what we're going to do is we're going to create this Hamiltonian based on this list. So this list is a simple representation of our Hamiltonian. So we're going to iterate over all the edges and create a ZZ operator for each of them. Like we said here, so that'll allow us to minimize or maximize over the function based on whether they're in different groups. And so this is handled by Qiskit. So Qiskit will handle it by using this function here from sparse lists. So that's what we created here. And then we'll create a Hamiltonian based on these number of edges that we created. So it's a very helpful function. In this case, we created a very simple sparse list because we use just a JIJJ where the edges are all of equal weight. But in more complex problems, this function will be very useful for creating your Hamiltonian from sparse lists. And so you can see here, we've created our cost function Hamiltonian, where all the coefficients are as 1 because we're doing an unweighted problem. And we have a number of different pairs that are listed based on the graph. And so next, what we'll do is we'll quickly print it out. So what we do is we use this function QAOA ansatz. And so this will construct this ansatz here. And that's just our quantum circuit with 3 parameters. You can see them here, gamma and beta. We do list some number of reps. And so that just means the number of iterations that we will use of our layers. So there's 2 types of layers that we use in QAOA. They're sometimes called the mixer array, and the other one is called the cost array, or the cost layer. So in this case, they're just going to be these operators, exponential of this times the Hamiltonian, and another exponential. And so what they mean qualitatively, these layers, is that one will try optimize it over the cost function, and this other one, the mixer one, will try vary the solution by a certain amount so that it's not getting stuck in local minimums. So it'll explore all the solutions to the problem more broadly rather than just focusing on one subset of solutions. So using the QAOA ansatz, we'll generate those operators. We'll be using just our cost Hamiltonian for generating them, and the mixer Hamiltonian will just be a general mixer. We don't need to worry about that. And we'll just do it by 2 layers with our 3 parameters, gamma and beta. And we can check the parameters are working properly. And so the next part of the problem, this is part of a standard workflow problem for quantum computing, is that we'll have to optimize the problem for quantum hardware execution. So different quantum computers will have different setups. They'll use different native gates. And so we'll have to use a transpiler. And all that does is converts the overall ansatz here into a number of gates based on the available gates for a quantum computer. So these differ based on the type of implementation used. That's why Qiskit is useful, because it's hardware agnostic. It doesn't matter what type of quantum computer you're using. You can generate the series of gates based on the hardware implementation of said quantum computer. But today we'll be just using an air simulator. So this is just a simulator for ease of use. So we'll generate a transpile error circuit, and we'll receive a number of different gates that we can run that is equivalent to our ansatz. And so the transpiler is doing a few things on this step. So first is mapping the qubits to the different pairs in our problem. So it might make sense to put the different pairs in different orders. So we'll do an initial mapping. Then we'll do the unrolling. This is what I was talking about before. We'll apply gates based on the hardware being used and the native gates that are possible to be used on said hardware, quantum hardware. And then it'll optimize over which ones are interacting with each other, because sometimes qubit 1 and qubit 4 are not connected, or sometimes they are. So the transpiler will determine which qubits need to interact and then create the quantum circuit based on that. And quite often we'll use error suppressions by adding single qubit gates to suppress noise while with dynamical decoupling. There's also other error mitigation techniques that'll be used so that some qubits sometimes aren't waiting or sitting idle for too long so that they lose some of their information. And next, we will use execute them with Qiskit primitives. And so what we're doing for the Qiskit primitives is that we are going to be embedding them in our workflow. So we're going to create some initial parameters for our free parameters that we'll be optimizing over. And then we'll create this loop that we were talking about before in our variational quantum algorithm that will allow the quantum computer and the classical computer to work together. And so what we need to do for that is create a cost function estimator. So in this case, we'll create our cost function estimator. That's just going to estimate some expectation value. So it's going to calculate an expectation value based on our Hamiltonian in our circuit. And we're going to use that for our ANSAT circuit for generating our free parameters. So this is going to be primarily used by assign parameters. So it's going to assign a different variety of gammas and betas, our free parameters, our circuit, and then compute the expectation value as before. So that is the estimator function, and is it here? So estimator that one. So that's going to use the estimator. As well as the estimator, I'll remind you that you can use a sampler. The sampler will generate bit strings, and estimator will generate an expectation value. And so that will generate some random costs so that we can determine how good our solutions are later on. And so let's do this. Let's solve this max code problem. So we will store how good of our solution are in our objective function values. We'll run our simulator using the estimator function. And then we'll try and minimize the cost function based on the results that the estimator returns. So what we're doing here is we're starting with our guess parameters. We're minimizing using some minimizer, in this case ClearBlock from SciPy. And every time we do this, we're executing our quantum circuit, which is the QAOA, getting a function back, and then optimizing over these free parameters. So you can see here that this is a success, and we can plot the cost of the function over the iterations. So let's run on and we'll regenerate this result. The cost in this case is going to be how good a solution is. The iteration is just the amount of times that we are working through the problem, getting different results, and getting a hopefully low enough cost that represents a really, really good solution to cutting our max cut problem. So let that run for a few seconds. There we go, we've got our solution here. So we have a cost of about minus 2.5, and that's just arbitrary based on our cost function estimator here that we did based on creating an estimator, running it, our quantum circuit using our estimator, and getting our results and determining the cost. So you can see here, we try different free parameters, and suddenly we find better and better free parameters until we get a very low cost, and that represents a good solution. So we found optimal parameters for our circuit, but how do we convert those optimal parameters and the result, or the bit string result, into a solution, into the graph solution? And so what we'll do is we'll create our optimized circuit. This time what we're going to do is we're going to use a sampler. So this circuit is going to be using the parameters we optimize over. We're going to run it with the sampler. And all that is going to do is it's going to return a bit string. So it's going to return a series of zeros and ones. And it's our job to understand what that bit string means. So you can understand what the bit string means based on the problem that we were talking about earlier, and how that the different 0 or 1 represents a cut in an edge based on the order they come in. So we'll run it on our sampler with the we're on the sampler with the optimized free parameters, and then we'll do it many times so that we can get a strong array of the possible solutions. We can create a distribution based on them. So we're going to get the distribution, and then we're going to convert it into integer counts. So, as I just said before, because we're using a sampler, we're going to get this distribution of different results and then convert it to counts. So we're using this quasi-distribution just because we're using the simulator, so that will generate the same result every single time for a circuit. The same wave function, but not necessarily the same bit string. So we'll just generate a quasi-distribution based on that. So, as I said before, we need to post-process this and return it into our classical format, i.e. into our graph. So, first thing we'll do is we'll convert our bit string into our results into a bit string. So our distribution here, you can see the method here. We'll convert it into a bit string, the most likely one into a bit string. So you'll see here, we'll select the most likely result, convert it into a bit string, and then we just read in reverse, just based on the notation or the order that IBM uses for their quantum computers. So you'll see that further above. What we'll do is we'll visualize and determine how good of a cut this is. So this is our distribution of bit strings of results. You'll see here, these are the best results. So we determine how many cuts each of these bit string results do. And as you can see, all four of them, so they all have the same amount of cuts, but they're in different configurations. So you can start off in different places or do it in different orders. These are our best results. And our most likely results are all results that are the optimal solution to our max cut problem. As we go down in probabilities of states measured, they are quite often good results, but not necessarily the best result. And so we'll draw our graph from before again. But this time, what we're going to do is we're going to label our different nodes so that we can evaluate a cut. So for this one, we're going to label them in grays and purples, as I said earlier. And you can almost see some of the cuts coming through. So there'll be no cut between this edge here, because they're both purple, but almost all the other edges allow a cut within them. But we need to evaluate this. We need to calculate what this actual number of cuts is. So we write a Python function to calculate what that cut is. So using some arithmetic based on what groups each of these nodes are in, whether the edge between them is a valid cut. And so, as we said before, it's 5. So let's check that just visually on the small graph. So we've a cut through there, that's 1. Cut through there, that's 2. Cut through there, that's 3. Cut through there, that's 4. Cut through there is 5. And that there can't be a cut. And if you want to, you can generate all the other possible solutions by working it through in your head or on a piece of paper on labeling each of these nodes in other graphs, and you'll find the max value is 5. And all these different ones that are highlighted in purple are a result of 5, but they're just in different orders which ones are labeled purple and grey. But they all return the maximum value of 5. And what we can do now is we can just test our knowledge. We can generate a much, much larger graph, and we'll generate a random graph for this problem. And you can see just almost immediately, once we go up to 20 nodes, the graph becomes a lot more complex. And even though there's not that many different options, so most of it's just circular in nature, even though there's only a few different cuts here and there, the number of solutions still grows drastically larger. And that's why we need to make run it on our quantum computer to make it possible to solve these problems. So, as before, we'll just go through the steps just for a reminder on how we solve these QAOA algorithms, how we run them. We'll generate our sparse list based on our graph. So, building the max cut parities. This is a function we used earlier. So it's just going to be a number of ZZs based on which pair we're using. So there'll be a ZZ for 0 and 1, there'll be ZZ for 1 and 2, and then there'll be a few more for these instances where there's multiple connected to each other. We're going to use an unweighted problem. So each edge is unweighted, they're all the same. We're going to draw our circuit. Now, we're using a simulator. So if we weren't using a simulator, it would generate some random circuit initially. But because we're using a simulator, we'll just draw the ansatz, so it just looks a bit narrow. That's why it says you can't add the measure all before transpilation. So we're doing that with the QAO ansatz again. So we're just doing one layer this time. So one layer of cost, one layer of mixing. This is possible because we're using a simulator. If you're using an actual quantum circuit, it might be more beneficial or a harder problem to use more layers. We'll then use the transpilation again. So we'll generate. So using generate the pass manager, we'll optimize it over one time. We'll create our circuit. We'll use the native gate sets. We'll make sure the qubits we want connected are connected in whatever order. And then using the estimator, we're going to find the free parameters based on our cost function. So it's going to generate the expectation value at the end of the circuit with different free parameters until it finds one with the best expectation value. And once it's done that, using the free parameters we evaluated with the estimator, so the cost function estimator, so the Qiskit primitive estimator, we're going to use the other Qiskit primitive sampler. And the sampler in this case is just going to be generating the bit strings once again. So you're actually running the circuit with a sampler, so like you would in real life. Whereas with a estimator, you can think of it as running the circuit thousands of times and generating an expectation based on that result, so almost an average. So using the sampler, we'll generate our bit strings. We'll actually run the circuit for many, many, many counts. We'll see once again that as we iterate over, our cost function is reduced until it hits a stable enough level. So by passing it through the circuit multiple times for multiple iterations. And then, based on that, what we can do is we can once again label our graph with the different colors using the best solution. And this is what quantum approximate optimization algorithm is all about. It's about taking advantage of the fact that classical computers are good at optimizing over parameters. So there's so many different methods of optimizing over free parameters that can be used in a classical computer, but they're not necessarily good at representing the full solution space for very complex problems. That's where quantum computers are considerably going to be a speed up or much easier to represent problems in, is because they're able to represent these solution spaces a lot better. So they're able to carry through the problem the number of solutions that are possible throughout the problem much better. And so once again, we'll confirm the value of the cut, so the amount of different edges that are possible to be cut through. Part is that we check how good of our objective function value is, like what cost is most likely. And you can see that the graph is very narrow, about this 25 to minus 10. So that means, as you can see here, the spread shows a range of objective values of the samples in the final distribution. And we want to see it jump at the lower end, so where the cost is very low. And that means we've run a good simulation because we got a lot of solutions with a low cost and a high probability of being sampled. And because it's smooth, it's because we're using a simulator, so we can generate these samples with a good distribution. And so that is all for this tutorial on the quantum approximate optimization algorithm. I hope you've enjoyed, and I hope you'll stay in touch by watching our other lectures in this TPSA lecture series for the Qiskit Fallfest 2025. Thank you.